Good morning and a warm welcome to those of you who have joined us here this morning in person, and a warm welcome to all of those of you online. We're starting this morning's session off with a talk by Zhenzhou Hui. He's talking on teaching resources for virtual observatories. Zhenzhou, over to you.
So I can start my talk?
Yes, you can.
Okay. Good morning and a good day, everyone. I'm Chen Zhou from Chinese Virtual Observatory, the National Astronomical Observatory of China. And today, I'm very happy to give an overview talk about teaching resources of the virtual observatory. In my talk, first I will give a very brief introduction about a virtual observatory and the IVOA. And then I will give much time for the resources for virtual observatory, including different abstracts. For example, the IVOA website, wiki pages, curriculums, and tutorials. The third part of my talk is about resources for astroinformatics. I will also give a very brief introduction about the resources about astroinformatics. And then I will conclude my talk using a special epilogue. First, this is, and all of us know, astronomy is a data-driven science now. About 20 years ago, the astronomy has stepped into the TB area, driven by several astronomical projects. Here I listed several examples, including the 2DF, the SDSS, LAMOST, and Gaia. Now, the astronomy is stepping from TB to EB area, driven larger and ambitious astronomical projects. For example, the 500-meter radio telescope in China and the future fast array, the coming SKA, the Vera Rubin Observatory, SST Sky Survey, the Euclid from the European community. Astronomy has been driven an engine for big data in science. And astronomy is entering an area of big data where the data sets are too large to download and analyze using users' own facility. So to satisfy the challenges facing the astronomical research, about 20 years ago, the idea of virtual observatory was initiated. Here is a vision of the VO. The web is transparent, and the goal of the virtual observatory is to achieve the same feeling for astronomical data. And astronomical data sets, tools, and services should work seamlessly together. The VO will allow astronomers to interrogate multiple data centers in a seamless and transparent way. Like the Worldwide Telescope, the VO is not a fixed system, but rather a way of doing things. Here, I give a brief definition for the virtual observatory. It is a data-intensively online astronomical research and education environment, taking advantages of the advanced information technologies to achieve seamless global access to astronomical information. In 2002, the International Virtual Observatory Alliance was created as an organization that debates and agrees the technical standards that are needed to make the VO possible. It is a focal point for VO aspirations and a framework for discussing and sharing VO ideas and technology. The Alliance currently has 22 member VO projects and has 6 working groups, 8 interest groups. Each year, the IVOA will organize 2 interoperability meetings. The first one in May, and the second one will be in October or November, usually together with IDAS. Next week, the IVOA interoperability meeting will be held online. Currently, about 26 interoperability standards or protocols have been defined by the working groups and interest groups of the IVOA. Talking about teaching resources of the virtual observatory, the IVOA website and wiki pages should be the first entrance. Here, I give the address of the IVOA website. Here, you can see we provided contents for astronomers, developers, members. From the website, you can get different kinds of information about VO and the scientific requirements, the latest progresses. Especially since 2000 and to the latest current 2021, you can find all the slides, programs, and related events materials about the IVOA. They provided a very comprehensive history and achievements by IVOA and its VO projects. Additionally, at the IVOA wiki pages, you can find the information about IVOA interest groups, working groups, and other materials. So the IVOA website and the wiki pages is the first entrance point for you to learn virtual observatory. At the IVOA, we established a dedicated interest group for education, the IVOA education interest group. Here is a URL for the interest group. You can get the background information about this group. In 2018, the interest group released a working note entitled Education Resources in the Virtual Observatory. These documents try to provide a registry-based solution for viable VO education resources. It is a very good solution. However, it is a little difficult for general teachers and VO educators. So this year, we created a usual wiki pages existing IVOA education resources and tutorials. All the related information and the new COMS information will added or linked from this wiki page. So your contributions are very welcome. Just send a URL and a brief introduction about your education tutorials or resources. In 2007, the first book about a virtual observatory was published by ASP. It is a achievement from the NVO, the National Virtual Observatory, in 2004, 2005, and 2006. The USVO development of product presented some schools in Aspen, Colorado. And this volume is a collection of the some school lectures and tutorials. And these materials are still relevant. In this book, it includes 59 chapters and 3 appendix, covered almost all the aspects of the virtual observatory and the related topics. So it is a very valuable reference for VO education and the developers. The Chinese version of this book was published 2 years later in 2010. As another creator of the IVOA, EuroVO is also an active member to provide education and scientific tutorials for the community. Here is a web page and the URL for the EuroVO scientific tutorials. This is the latest tutorials, and at the same time, you can also find the previous tutorials and the interactive Jupyter notebooks here. For education resources, the EuroVO project provided the EuroVO for education. It is a project by the EuroVO with the aim of diffusing EuroVO data and software to the public, in particularly students, teachers, and astronomy enthusiasts. The EuroVO resources are now maintained and upgraded by the Italian VO. Yeah, you can see here are a list of the education samples. First, these samples will guide you scientific requirements, and then there will be a step-by-step guide to the commands needed to reach the solution of the problem. And they also provided in several different languages for the samples. Here is an example from the Columbia Darien. He used Cassis for updating the tutorial provided by EuroVO education, calculating the redshift of galaxies. And this updated version will also be found online at the EuroVO education project. CDS provided the cornerstones for the astronomical research and the virtual observatory using its 3 services, the SIMBAD, Visera, and Aladdin. From the CDS website, the CDS also provided the detailed tutorials for SIMBAD, Visera, and Aladdin. And you can also see, you can also find some other materials for developers. The Spanish VO is also very active for education and scientific teaching. From the website of the Spanish VO, we can get teaching astronomy with VO materials for undergraduate and graduate projects, and SVO schools and meetings. Here you can see the links for the tutorials, education thesis, and the SVO meetings. Later of today, Francisco and James Esteban will give a talk, especially for the European Virtual Observatory schools. So you are very welcome to attend his talk. German Astronomical Virtual Observatory also provided very helpful tutorials for VO educations, including the ADQL reference card, the ADQL hands-on course, and the Gavo tutorials. Here you can find the link. I will share my slides at the IDAS website, so you can get all these URLs. Armanian VO is also another active member for VO education and teaching. Here is an example. They organized two very successful meetings, summer schools last year. Here is this one is the International Summer School for Young Astronomers with the title of Astronomy and Data Science. Another meeting is Astronomical Surveys and Big Data. Here is a screen capture of the meeting and summer school. You can find the slides and the lectures. This is a URL for these two events. Additionally to these English materials, since there are many other non-English speaking VO projects, here I share some with you. The first one is from the Japanese VO. Since 2006, the JVO organized several unusual schools for VO for students and graduates. Here is the link, and each time they also provided the slides and the PDF for their materials. It is useful for Japanese, or if you can learn Japanese, yeah, it is very helpful for you. For the Chinese Virtual Observatory, we start the annual meeting since 2001. During the last 20 years, we collected a lot of slides and teaching materials. Here is the programs for the last 3 annual meetings. These slides and tutorials provided a very comprehensive history and achievements for the Chinese Virtual Observatory. And this year, we will have the annual meeting in early December. Additionally to the annual meeting of the China VO, we also provided a public channel for our users, especially including the Worldwide Telescope, the Community Beijing, and the PSP Citizen Science Project, the IAU Depot Working Group, ESA Sky, and a number of other useful services and tools for public for the teaching and education. Next, here are some brief resources for astroinformatics. Astroinformatics is a closed community with the Virtual Observatory. So these resources are also helpful and useful for VO teachers and educators. First, there are 2 portals very useful for astroinformatics. The first one is a portal from International Astroinformatics Association. They provided useful links and resources, including general data science and astroinformatics, software resources, learning resources, and lecturers, funding opportunities. Another one is the Astrostatistics and the Astroinformatics portal. In their portal, they provided a comprehensive online courses for astroinformatics use.
Connection. Okay. Apologies for the interruption, folks. It appears that we have a few connection issues to the speaker. We are trying to reconnect to him. Apologies for that, folks. It appears that we have lost a speaker. You can continue your questions in Discord if possible, and yeah, we'll have a discussion over there. Sorry about that. Okay. The next talk is going to start in about 5 minutes, yes, that's going to be presented by Stephen Potter on the Intelligent Observatory, the South African Astronomical Observatory. So stay tuned. All right. Next up, we have Stephen Potter. He's presenting the Intelligent Observatory, or the South African Astronomical Observatory. Peter, Stephen, the floor is yours.
My name is Stephen Potter. I'm an astronomer at the South African Astronomical Observatory. I also hold a visitor's position at the University of Johannesburg. And before I begin, I'd just first of all like to thank the organisers for giving me the opportunity to speak to you all today. And I'm going to talk to you, I'm going to present to you a project we... Hello, my name is Stephen Potter. I'm an astronomer at the South African Astronomical Observatory. I also hold a visitor's position at the University of Johannesburg. And before I begin, I'd just first of all like to thank the organisers for giving me the opportunity to speak to you all today. And I'm going to talk to you, I'm going to present to you a project we have ongoing at the South African Astronomical Observatory called the Intelligent Observatory. This is in fact a joint program between the SAO and the South African Radio Astronomical Observatory. So there are 4 parts to my presentation. I'd first of all like just to start, set the scene behind the Intelligent Observatory by describing to you SAO's part in the gravitational wave GW170817 event in 2017. So as you may remember, this event, which resulted in gravitational waves being detected at the LIGO Virgo Observatory, was as a result of the merger of 2 neutron stars. But what was unique about this event was the fact that not only were gravitational waves detected, but a couple seconds later, short gamma ray bursts were detected independently by the Fermi and Integral spaceborne satellites. So this then was preceded by a worldwide effort to identify if there was any optical counterpart to this event. And it was the Schwope telescope that first identified the optical counterpart. And then once those the coordinates of those optical coordinates were made known, there was a worldwide effort to follow the course of this event. And that's what we did at the SIO. So this image on the left is an image made with our 1.9 meter telescope at the observatory in Sutherland. You can see there's the optical counterpart on the host galaxy. And the image on the right is an image taken again with a 1 meter telescope, but 2 days later. And you can see just after 2 days, the optical counterpart was no longer detectable by our 1 meter telescope. We also have an infrared facility in Sutherland, and this continued to follow the optical afterglow at infrared wavelengths. And you can see, here's the infrared image on the right, and there's the infrared counterpart. And even though this is a modest sized telescope, this demonstrates quite nicely the importance of multi-wavelength astronomy, because even though the optical counterpart had disappeared quite rapidly over just 2, 3, or 4 days, there was infrared light visible for almost pretty much 2 weeks later, even for a modest-sized telescope like that. And then, of course, at Sutherland, we also host the Southern African Large Telescope, and we were one of the first observatories in the world to obtain an optical spectrum of this event. And this optical spectrum was combined with other spectra taken from other observatories across the world to follow the spectroscopic evolution of this event. And then all these observations were finally combined to make the first so-called multi-messenger observations of a binary neutron star merger. And the thing I'd like to highlight here is this publication consisted of over 3,600 authors from over 700 institutes. And this is a clear demonstration of how important this multi-messenger event was, and also how much coordination and collaboration it took to get all these observations together to make the final scientific publication. So that sets the scene. So what's this got to do with the Intelligent Observatory. So I'd like to talk about the vision behind the Intelligent Observatory, why, what, and how this is all about. So in a nutshell, the reason why we're doing this is because we basically want to better serve the community and users of all our facilities in Sutherland. But this not only means, I'm not only talking about individual astronomers here, I'm talking about the plateau providing a service to other facilities, such as the LCO, or the Gaia satellite, or the Gamma Ray satellite, or the LIGO Virgo observatory, for example. So we want to provide a better service to everyone and everything. So what exactly is it? So basically what we're working towards is having all of our telescopes on the Sutherland Plateau integrated into an overall intelligent observatory, and thereby allowing us to better coordinate science across all of these telescopes in the so-called era of multi-messenger astronomy. And that will enable us to respond better to alerts and other computer-generated requests. And it also requires us to automate a lot of these processes, and not just telescopes and instrumentation, but also the management of proposals and things like that. So basically, this program is advancing the SAO into the so-called fourth industrial revolution. So how will we do this? How are we doing this? So there are kind of 4 overall work streams. The first being consisting of all the hardware and software upgrades that we'll need to do. So for example, our telescopes and facilities, in particular our own workhorse telescopes, we need to upgrade the hardware, the electronics and software so they become more automated and more robotic. Another work stream will be the data science software services that we provide. So rather than providing recipes for data reduction, we'll need to upgrade the software such that observations from telescopes will be automatically processed through pipeline solutions, so in order to enable quick look on the fly data analysis. A third category would be the kind of intelligent algorithm aspects of the intelligent observatory. So this will be the software algorithms that will make intelligent decisions behind things like alerts that might come from LSST or Meerkat or the LIGO Virgo facilities, etc. And then finally, the fourth work stream is that we're going to have to overhaul the complete management of astronomy operations and telescope operations across our facilities in Sutherland to better accommodate the vision behind the intelligent observatory. So I just want to talk about the sort of telescopes that we briefly talk about the sort of telescopes we have in Sutherland, just to give you an idea of the challenge that we have behind us. So we have, there's kind of 3 workhorse telescopes that the SAO fully owns and is available to the whole international community. There's 2 rather old telescopes. There's the 1.9 meter telescope is over 70 years old. We have a 1 meter telescope that's about 50 years old. And we have another new 1 meter telescope, which is about 4 or 5 years old. And between them, they have a suite of instruments that are capable of spectroscopy, polarimetry, imaging, and a speciality of ours has been high-speed imaging. We also host, of course, the Southern African Large Telescope. The SIO for the National Research Foundation is a partnership in this facility, and this is a Q-scheduled service observing telescope. And in addition to these 4 telescopes, we have a range of other telescopes. Some of them we purely host, they are fully automated or robotic, and some of them are partnership telescopes, like for example, the infrared facility is a partnership between the SAO and some institutes in Japan. Okay, so the final section of my presentation is where are we in this vision right now? What is our current status? So at the beginning of the program, we were in a situation where if you wanted to use the facilities in Sutherland, you either had to go to Sutherland yourself in order to use those workhorse telescopes that I described earlier, or you would contact, say, the LCO network to submit proposals to the LCO telescopes, or if you were you would have to contact the other host facilities if you wanted to get time on those telescopes. Since the project has begun, we have now upgraded all of our workhorse telescopes, even the telescope that's over 70 years old, such that now we provide remote observing capabilities. And now we can control these via software. There's no reason now that we can move beyond just humans remotely operating these telescopes, but they can be robotically or automated in some way. So the next step that we're working on now is making these facilities as a service that are not only available for astronomers, but also to other facilities in general. So for example, the Vera Rubin telescope through the LSST program will provide an alert service. So we will want to enable the Intelligent Observatory will intelligently analyze those alerts and send requests to an appropriate suite of telescopes to do follow-up. The same goes for the LIGO Virgo alerts and also other spaceborne systems like the Gamma Ray observatories and perhaps also the Gaia facility as well. So to do this, we're building what we're calling a central control system. And at the core of this central control system is going to have to do all these sort of things. So this is just a list of what I've already described. For example, there's one telescope, this one over here called MeerLicht, that will simultaneously obtain an optical image of wherever the MeerKAT telescope is coming from. So if this telescope in real time detects an interesting optical counterpart to a MeerKAT radio transient event, it would then send an alert request to our central control system to maybe obtain a spectrum from using the SALT telescope or polarimetry using the SALT telescope, or maybe to continually follow it up with high-speed photometry with one of our 1-meter telescopes. So that brings me to the end of my presentation. If you'd like to know more about the Intelligent Observatory, there was a rather nice write-up in Physics Today earlier this year. We also have a website where you can obtain more project-orientated information. And also there's my email address if you'd like to know more. And that's my presentation. Thank you very much for listening.
Stephen, thank you so much for that talk. I'm going to start off with any questions from the floor. Seems we don't have any questions from the floor. All right. There is, okay, so I think Peter asked a question. I think you addressed that. So he asked, so there's so many telescopes near each other, and look at this cute stereo all-sky gadget. So, and I see you responded to him there. There are sky brightness monitoring cameras, and yeah, so there are two of them apparently. So Ruby asks, we're on Discord, Steve, can you comment on the future vision of trying to, in the partner telescopes on the plateau towards building multi-wave astronomy in SA?
Yeah, that's a very good question. Thanks for that. Yeah, so one example that I gave during my talk was linking up with the MeerLicht telescope, as you know, which simultaneously monitors the sky with MeerKAT. So there's the multi-wavelength connection there. And also we're going to try and offering to link up with any facility around the world as well. So we're part of the the kind of in-kind contribution to the Vera Rubin Observatory. So part of this Intelligent Observatory project is to make the observatory AON compliant, such that we can better connect into their alert services and to their scientists as well.
Thank you. I see Peter is typing another question here. Just posted that. Okay, so perhaps stereo, so you can see the clouds in 3D. So I'm not kidding. We have a single all-sky camera, and we can see clouds moving at different heights in different directions. I guess this could mean something for the quality of the night. So just comment.
Great, thanks. Yeah.
Nicholas is typing here, so let's wait for that to arrive. Any questions from the floor? None so far. Right. I think we're going to take Nicholas' question offline. Stephen, if you can just respond to him there. Thank you so much for the talk.
Right, thanks everyone for listening.
All right, so next up we have Bernie, and he's going to, so she's going to be describing free workflow add-ons to improve machine learning reproducibility in astronomy.
I'm Bernie Bosco, and thank you for having me here at ADAS. And I will be talking today about 3 workflow add-ons to improve machine learning reproducibility in astronomy. So this talk, I'm thinking about small to medium astronomy research groups who might be incorporating machine learning into their workflows or thinking about it, possibly lucky enough to have a computer or data scientist or a tech person on their team, or not, and who are interested in these cultural considerations of crossing domains. For example, what are machine learning needs from industry or from places that are not in astronomy versus what does astronomy need for doing machine learning and the practices and tools that would entail. So a little about me, I'm a computer information scientist. So I work with astronomers and study their data and code practices. So right now I'm working with an astronomy team at UCLA who are doing machine learning projects. And specifically, we're looking at predicting galactic redshifts using PhotoZs and machine learning. So before machine learning, let's go back in time to 1995 at, you guessed it, ADAS. So in the beginning of digital astronomy, what I'm calling it, so maybe we can say this started in the 1970s, astronomers have been designing and building their own instruments and software tools since this time. And most famously, I think, is designing the FITS file format, which has been well represented at these birds of feathers at ADAS over many years, starting in the 1990s. And so during these bird of feathers, they would be debating, do we modify FITS? Do we keep the same? Clearly, we should always have it be backwards compatible. But what does that mean? And what does that look like? And what types of issues are we addressing in the FITS file format? And so I will point this out as one who studies other scientific domains. Most scientific domains do not have their own file format, let alone the plethora of trusted tools built over the years. As you would know, IRAF, FITS, systems like IDL and languages like Fortran used in the process of building these. And so I always tell astronomers they're very spoiled by having this infrastructure, digital infrastructure to use. But now we have seen as it ages over the years, astronomers might be a victim of their own success. Now we have these tools that are well beyond what they were expected to last. And so now new decisions have to be made about what to do about these things. And I write about this. If you're interested, that's one of my papers at the bottom in the history of computing. So one of the research questions that I think about is, for this project anyway, is so when astronomers adopt tools from other open source and industry domains to incorporate into their machine learning research, what can we learn from this, and what does that look like, and what are the pitfalls, and what are the benefits of doing such work? And so in particular, I'm studying when astronomers use tools like TensorFlow or PyTorch, as opposed to these bespoke solutions like building them, or astronomers are doing a combination of both. They might be using TensorFlow and building their own C++ algorithms that might go along with TensorFlow. And so this crucial point is something that I've seen and lived and realized over the years, is that most of this machine learning code and these infrastructures and tools, most of anything that you would build now will likely not run in 5 years' time. And our team has done this. We've tried to rerun projects from just a few years ago. For example, the Chalou and Vandenberg exoplanets deep learning project. So that's from 2018, and we had so much trouble even replicating this study. And they were very generous. They gave all of their code and everything in a GitHub repository, and the survey is public, so you would think this would be easy. However, you had these competing libraries, which then you have all of these conflicts, and then do you deprecate one, or do you upgrade the other one, and getting everything to talk to each other when you have all of these dependencies. It was very difficult. So this is just something to consider if you're considering incorporating machine learning into your work. So my first suggestion here is add-on number one, which is versioning training data. And so Evan Jones, my colleague, has a poster in ADAS this year. So it's called Building a Training Set of Hundreds of Thousands of Galaxy Images. So this is this arduous process of how do you get all of these images for a training set? Because as you would imagine, just querying a survey and collecting all of the information, that's not machine learning ready. And to get these things into the form that we need them to is a lot of work. That data munging piece is the part that nobody wants to do, it seems like. And so what we thought about in this is what was done in the initial query, like what were the quality cuts that were done, and then our question was, when do we make a new version? And the granularity is key here. How much changes were made, and then what would that mean in terms of versioning the thing? So we chose to make a new version when the total number of galaxies changed. And for example, we had these redshifts greater than 2.5. They were not very well fit, but we kept them in the version because we wanted to keep this training set to have an underlying sample that would remain the same. Because with our machine learning processes, we can augment these balances and change them, but we wanted to keep that distribution that is from the survey itself, and that was challenging to do. So for example, we deleted duplicates that we found, but we tried to keep that underlying distribution to be the same. So number two, saving models themselves. So for example, one might save a scikit-learn model with Pickle, which is a Python-based serialization tool. And you could save these and use them later. It's very easy to use. However, there's no way to know what are in these files because they are serialized. They are unsearchable. So if you save things in Pickle, but you do not know what you saved in Pickle or who did this, if you're working on a team, or when or how, you have a problem because you don't know what it is. These also have security issues. For example, one should not open a Pickle file that was emailed to you, for example. And they can be slow, especially if you have something that's a very large model with a lot of weights and parameters in there. This could be very slow. So if we look in this space of, in this case, I'm using TensorFlow as an example, you have TensorFlow.save, model.save, you have model.save weights, and then there's all of these different ways that you can save models. Plus you have the different file formats like saved model, which is a TensorFlow proprietary format, or the classic HDF5, which I assume that ADAS folks are familiar with. And then you have these low level versus high level model type saving implementations. And these depend on your API. And so Keras has taken the world by storm in the past couple of years. So now their new models are added on to the quote unquote older versions of TensorFlow saved models, which are now deprecated. So my point to astronomers is these tools were made by people moving fast and breaking things, and they're not built to last on purpose. These are built for deployment in industry, and they're made to be used to predict car part sales or whatever. So clearly you're going to improve upon your model, and you're not going to keep something from the past that has been improved upon, which is not what we're doing in astronomy. We need things over time to be stable and to be replicable and reproducible for our work. And so my question is, what do astronomers need to save in models? And also, what do you not save? So we can't save everything. That is not practical. And so we might want to document these failed architectures, but not save them. We definitely want to save the models that we use for publications and document what is in these models, and then the TensorFlow version that it's created in. And this is more for transparency, because most likely we would not use the same model again in the future. We would probably find something that is better, or we would improve upon what we have. And so in terms of these gotchas, you might be thinking, why not put it all in a Docker container? Well, that's a good question. You could, but I have found in my experience, the learning curve is a bit steep with teams. Also, Docker is starting to charge $7 a month per person for teams. This is brand new. And for us in academia, this is hugely problematic. We're trying to use things that are free, right? Or cost very little money. And this is a huge problem, the way that I'm looking at incorporating Docker into workflows. Again, Jupyter Notebooks might be nice as a recipe of steps, but again, Jupyter too has its own difficulties, has a very small group of maintainers, believe it or not, and is relying on a backbone of aging code. And so this is an issue. This has come up this week in GitHub. It's being discussed what's going to happen to the Jupyter Notebook. And then obviously you have Microsoft, involved in these issues, and then Colab and other tools that have been adopted from this. And what does that look like? And so for add-on number 3, these additional artifacts. So FITS files aren't designed for machine learning. We know that. And there are tools like AstroPy that might help get FITS files and images into a model. But we could also put some of this information back into FITS to preserve it if that is something that people are facile with doing and they're familiar with the tools. And astronomers might need additional artifacts that are not needed by these machine learning practitioners, such as predictions per galaxy. Machine learning in the wild, in industry generally, aggregates are good enough. And in astronomy, uncertainty measurements rule the roost. These would not be something that is in machine learning traditional practices in the computer science realm. But hyperparameter choices and weights would be, so the combination of these would be something that astronomers might think about using. And then preserving this metadata piece associated with your study or your paper and put it in a place like Zenodo, which I assume most of you are familiar with at this point. We found in our work that a lot of people doing all of the tinkering and the trial runs didn't save what didn't work. And I feel this would be useful to save too. It's all of these things that someone else tried and it didn't pan out. Good to know for the future about why models would go awry and not give you the results that you're looking for. And also a breakdown of looking at what metadata is for your team and then what is for public use for reproducibility's sake. So in conclusion, The documentation is time consuming, but I think it's worth it. And deciding on these storage formats is important. Otherwise, you might have a Tower of Babel of models in these different formats. This is not optimal, especially 2 years down the line, people leave your group, you don't even remember what they did. It's in a pickle file, and we all know that's not good. Working and publishing in these cross-disciplinary spaces means accruing these different types of evidence that are necessary for ground truthing and results. And what does that look like for your team? And then, as I pointed out, these information preserving needs, they vary between what you need to save for yourself, for your team, and then what you're going to share with the outside world. And thank you very much. And thank you to the Sloan Foundation for funding our research, and Spell ML for funding our machine learning runs. Thank you.
Bernie, thank you so much for a great talk. There's a hot debate going on Discord. I'm not sure if you're following there. I have a question from Jonathan Kenyon. Hi, Bernie. So you mentioned how challenging requirements and new technologies may make updating or changing a format necessary. Can you comment on the challenges you feel we face when attempting to make these changes?
I'm sorry, I didn't hear the first part of the question. Can you repeat that?
Sorry, he asked that you mentioned how challenging requirements and new technologies may make updating and changing a format necessary. Can you comment on the challenges you feel we face when attempting to make these changes?
Right. Well, for the astronomy community, I feel like everyone is generally used to a stable format such as FIT. You don't have that when you go into the machine learning space. And so to just be aware of that and to keep that in consideration is the point that I'm trying to make, is that these formats might go away quicker than you might realize, like TensorFlow.save or something. And so how do astronomers keep things in the way that they've always kept things is the question that I'm thinking about.
Okay. Thank you so much, Bernie. Another round of applause for her.
Thank you.
All right, so the next talk is by Sviatoslav Borisov. He's going to be talking on multi-segment and stellar spectra processing issues and how to solve them.
Can you hear me? So, can you hear me well?
Yeah, we can hear you.
So, hello everyone. My name is Sviatoslav Borisov, and currently I am a PhD student at the University of Geneva, and I'm also doing some research at Moscow State University. And today I want to tell you about some issues you might have when dealing with multi-segment and the stellar spectra, and the ways to solve these issues. Yeah, so the main motivation for doing this is that because we want to model stellar populations in galaxies and star clusters and etc. And especially it is very important to do this in the infrared range because the number of observations is growing in this range, and I believe that after the launch of the James Webb Space Telescope, it will start growing even more rapidly. Also, we need stellar spectra for some exoplanet science and for constraining the stellar evolution models. In my talk, I will consider two different stellar spectral libraries. One of them we developed by ourselves from scratch. As for the second one, we recalibrated the existing one. So, and I will start with Las Campanas Observatory Stellar Library, which we developed during the last several years. And this stellar library consists of spectra of approximately 1,400 stars, and it has a very good coverage in the space of stellar atmospheric parameters because it has observations of many different stars, including some very rare types of stars. For example, so far this is the largest set of infrared spectra of AGB stars. It also contains some spectra of stars from Magellanic Clouds, of brown dwarfs, etc. This library was observed with FIRE. This is a spectrograph mounted on Magellan Bade telescope in Chile. This is an intermediate resolution shell spectrograph, which covers a wavelength range from approximately 0.8 to 2.5 microns. And here you can see it's on the left figure, you can see its optical layout, which is very complex, which makes data processing very difficult. And now I will tell you more about these difficulties and solutions. So first of all, you might have some problems with the point spread function because it might be non-Gaussian, and moreover, it might be cut by Slayton 1H. And there is another type of problems is that due to some flexures in the mechanisms, the flat field frame might be a bit shifted with respect to science frames, and it produces some ripples in the regions where echelon orders overlap. So, but there is a solution to this. First of all, you have to use empirical PSF and perform optimal extraction using it. So, and as for this shifting of the flat field with respect to science frame, you need to derive the optimal value of this shift by minimizing the difference in flux in these regions where orders overlap. The second type of problems, it relates to detector and the instrument. The detector itself, it has 4 amplifiers, but they're slightly different. And it also might have some problems with pixels because they might be hot or dead, and they have different sensitivity. As for the instrument, there is one very crucial problem. Its slit position is not repeatable, which means that if you use one slit and then change it to another, and then change it back to the first one, its position is not going to be the same as the initial. So to solve this, you have not to change the slit position between calibrations and science observations. For example, we did calibrations in the daytime because we didn't need the dome open, so we could do this with the dome closed, and moreover, it saved a lot of time. As for the pixels, of course, you have to create a bad pixels list and to create super flat to correct this pixel to pixel sensitivity. The second problem is telluric correction. Telluric lines, they're produced by an Earth atmosphere, by oxygen and vapor, water vapor, and in the infrared range, it is also produced by methane and by carbon dioxide. And to eliminate these lines, you have to divide the observed spectra by atmospheric transmission models. But since these lines are very, very narrow, you have the wavelength solution should be just perfect. So, and if the wavelength solution is just a bit imperfect, it might lead to some very big residuals. The second type of problem with telluric correction is that the most common way to perform it is to observe spectra of so-called telluric standards. Usually they are fast rotating A-type stars, but they're not really standards. Why? Because they might have different rotational velocities, they might have emission lines in the spectra, and also some mismatch in between real atmospheric parameters and model atmospheric parameters is possible. So that is why we developed another method to perform this telluric correction without even using a telluric star. So we use a model which consists of synthetic spectrum and multiplied by atmospheric transmission and convolved with the line spread function. Also, it is possible to take wavelength shift into account in order to fix these imperfections in the wavelength solution. And then, so when we have this new adjusted wavelength solution and atmospheric transmission, we can just, as I said, divide the observed spectrum by this model. So the second stellar library is UVSPOP. Originally, it was developed by a team from ESO, and it was observed with UVIS, which stands for ultraviolet and visual shell spectrograph. This library contains about 400 stars and with a very high resolution of about 80,000 and covers a wavelength range from 0.3 to approximately 1 micron. But unfortunately, there are some issues with it. First of all, they relate to shell orders merging and stitching of non-overlapping segments and some other problems. So as for shell orders merging, as I already said when I was talking about LCOSL, it might be due to some shifts of the flat field with respect to the science frames. But we also, in this library, in case of this library, we also discovered a second reason, and this is over or under subtraction of scattered light in the spectrograph. So that is why you have to modify the initial algorithm a little bit and derive both the value of this shift of the flat field and the value of this over or under subtraction. And here in this figure, you can see the an example of this what we had and what we had before and what we had after this correction. Also, since the library, spectrograph has 3 different CCDs, there are some gaps between them. So, so that means that there are 2 gaps in all the spectra. But unfortunately, they were stitched not perfectly, which means that there are some jumps in the flux on the left side and on the right side of these gaps. So to solve this problem, we used synthetic spectra to adjust these segments, to adjust the flux on the both sides of the gaps. And here you can see an example with original and corrected spectra. We also performed parametric correction because anyway, after all the procedures, you still might have some imperfections in terms of flux calibration. So we collected data in 33 photometric bands from these catalogs, including 2 space-based catalogs, Gaia and Tycho. Of course, we don't have 33 observations for all the stars, but we collected as many as possible. So here you can see an example of this correction. We just adjusted the spectra to the photometric spectral energy distribution. So in summary, I'd like to say that we have 2 different stellar spectral libraries with a very high quality of flux calibration, and one of them is has an unprecedented coverage of the stellar atmospheric parameters in the space of stellar atmospheric parameters. And for most of the stars, we have the values of their parameters. And if you want, you can see the poster by Evgeny Rubtsov on the conference, which describes the minimization algorithm which was used for full spectrum fitting. And also visit our website of the project. Here is the link to it. And on the website, you can play with all the spectra, with fittings with the parameters. So you will find the table with all the parameters, and this is very, very user-friendly and nice, I hope. So that's it. Thank you.
Thank you so much. Round of applause, please. Peter made a remark here on Discord that I will just read out to you. Maybe you can have a comment there. The order merging is always a bad idea and never works. To get perfectly unblazed spectrum, of hot stars is impossible. Do you have any remarks on that?
Could you please repeat what is not perfect orders merging?
The order merging is always a bad idea and never works. To get perfectly unblazed spectra, sorry, another question has moved, sorry about that, of hot stars is impossible. Do you have any remarks on that?
No, I don't agree because for example, here you can see an example where merged orders, and this is quite hot star, and as for me it looks very nice. So it is possible to merge both cool and hot star orders of both cool and hot stars without any problems.
Okay. Okay, so yeah, a follow-up remark here. How do you save a shell spectrum to preserve all the precision? Usually people rebin the merged spectrum in one long strip, losing part. We do not have ideal format for storage of a shell, / the VO should start to work on it.
So the question is about rebinning.
Mm-hmm.
I guess it's so. I think the key point here is that you have to. I'm not sure that I'm answering this question, but first of all, you have to perform optimal extraction, and as for the rebinning, well, I don't think we had any specific issues with rebinning, but yes, of course, you have to do some rebinning to increase the signal to noise ratio.
All right, thank you. Perhaps we can take that offline. It sounds like an interesting discussion. Thank you so much. Can we have another round of applause for all the speakers this morning? All right, and I'm going to sign out. So, your host, Benjamin Ego here. So, the next session is going to start at 10 a.m. and Athanasius will be hosting that, and we look forward to seeing you there.
Hello, everyone. Welcome to the second session of the day. I'm Athanasios Ramaila, a software developer at Sarao, part of the Radio Astronomy Research Group. I'll be the session chair. Our first speaker of the day, our first speaker of the session is Andy Connolly from eScience Institute. He will be remotely presenting about scaling science in the era of survey astronomy.
Okay, thank you. It's a pleasure to be here, even if it is virtual and 1 a.m. on the west coast of the US. I guess being an astronomer, I shouldn't really be complaining about that. My name's Andy Connolly. I'm a professor in the Department of Astronomy at the University of Washington. I'm a member of the Dirac Institute, which is an astronomical data science institute housed at UW. And I'm also director of the eScience Institute. So the eScience Institute oversees the data science research and education at the university. So what I'm going to talk about today is about the scaling of science in the era of big data, and in particular, some of the challenges and the opportunities that we face with experiments such as the Rubin Observatory, which will be undertaking the Legacy Survey of Space and Time, or the LSST, and data sets that will come from experiments like the Square Kilometre Array. And this is really just to name two of the many experiments that will come online this decade and represents a many billion-dollar investment in survey astronomy. So first, I wanted to note that astronomy has always been a big data science, whether we're talking about the digitization of photographic plates using a 200 megahertz Pentium Pro computer to create a terapixel image of the southern sky, or whether it's the 250,000 lines of code that were written in the early 2000s to process the SDSS data to produce the first large linear survey of the Northern Hemisphere. The challenge in those days was the lack of computational resources, both in terms of CPUs, the numbers of CPUs, and the memory that was accessible through those CPUs. With cloud computing today, we're not really in the same position, at least for optical surveys such as the LSST. The data volumes of the LSST are small relative to the data volumes analyzed by the tech companies, and even small relative to the data coming from the biology and the earth science communities. Where we do face a challenge is in how easy it is for a researcher to make use of the data and the associated computational resources. So this is a really very broad field. So what am I not going to talk about? Well, I'm not going to talk about the data reduction frameworks that are being built to process Rubin and SKA data. We build experiments with the compute resources necessary to process the data and the teams to build, test, and validate the software. Instead, I'm going to focus on how we can go from calibrated images and catalogs to the science. And that's not usually a place where we invest resources until the data have actually been taken. Often when we discuss large data sets, we talk about it in terms of the 5 V's: the volume, the amount of data we're collecting and processing; the velocity, the rate at which we're collecting data, or the rate at which we serve those data to the community, such as the 12 million alerts we expect to generate per night with the LSST. We then complain about the variety of the data, meaning the data complexity, as we work with structured data, for example, tables of features, or unstructured data like light curves with varying numbers of observations and temporal sampling. And we also complain a lot about the veracity of the data, or the noise, or the calibration of the data. But I think in many ways we ignore the final V, the value or the information contained within the data. And what I want to talk about over the next 20 minutes or so is, if we think about the structure of the data and the physics of the problems we're trying to address, or the questions we're trying to answer, we can often reduce the complexity of the analysis that we want to undertake. This leads to a reduction in the computational resources needed, and also opens up the types of analysis frameworks that we can utilize. So by simplifying the data, or how we can efficiently represent or model it, which in itself requires a detailed understanding of the noise, we can begin to develop analysis tools that may be computationally tractable and usable by the majority of researchers, not just those with excellent coding abilities. So I'm going to illustrate this point with a couple of examples coming out of the work from the Dirac Institute at UW. On the left, you can see the distribution of outer solar system asteroids, or trans-Neptunian objects, or TNOs, And I'm showing them as a function of their perihelion distance and eccentricity of their orbit. There are about 2,000 known TNOs in the solar system today. The positions and the orbits of the TNOs trace the history of the solar system. As the giant planets migrated from the inner solar system outward, in doing so, they interact gravitationally with the planetesimals or the asteroids and scatter them into the outer solar system. The properties of the planetesimals, for example, the number of binary asteroids tells us about how dynamically hot this process was. The more dynamical the process, the fewer large separation binary asteroids are going to remain. So tracing the properties of the TNOs allows us to map the history of the planet, of the planetary migration, to see if there are other belts of asteroids beyond the Kuiper belt, to search for evidence for other large bodies in the outer solar system, for example, the Planet 9 searches, and potentially even to probe the properties of the primordial material from the Oort cloud. Traditional approaches for finding TNOs are to identify moving sources in individual images, as we can see on the right-hand side. In the real world, we don't have red circles on the sky to identify where the asteroids are, but the algorithms for tracking these slowly moving objects, and they're moving at about 1 arc-minute a day, the algorithms for tracking them are well known. And so LSST, using these algorithms, will detect about 20,000 TNOs over the period of 10 years. And this will increase the number of known TNOs by about a factor of 10. These algorithms, however, rely on the detection of an object in an individual image. So the searches are limited to the depth of a single LSST image, or about an AB magnitude of about 24.7. If, however, we knew the trajectory of the source ahead of time, we could shift the images to account for the motion of the asteroid and co-add the images to detect the asteroid at high signal to noise. And this is known as digital synthetic tracking. Unfortunately, we don't know the trajectories a priori, so we have to undertake many, and by which I mean billions, of blind searches, evaluating many candidate trajectories to look for evidence for a source. And this is really computationally expensive, and so it's generally only been undertaken for very small areas of the sky. But more recently, Peter Whittam and collaborators showed that if we pre-convolve an image with a PSF, we produce a likelihood image, where the value of the likelihood image at a given position just tells you the probability of a point source existing at that point. So now we can determine the likelihood of a point source being represented in a stack of images simply by summing up the log of the likelihoods. To search for moving sources, we can take an arbitrary trajectory and we can sum the log likelihood at the relevant positions in the stack of images. So we never have to get to a point where we shift and stack the images themselves. This maps very naturally onto processors such as GPUs with CUDA, where each potential trajectory that we want to search is an independent evaluation of a set of pointers within an image or within a set of images. So transitioning from a CPU to a GPU enables billions of trajectories to actually be evaluated. So we can evaluate about 1 billion trajectories for 15 4K by 4 images within about a minute. And if we couple this with a convolution neural network to remove some of the false positives, I don't really have time to go into the details about that, but I'm happy to talk about that later. We end up with a fast detection method for detecting our asteroids that are well below the detection threshold of a single image. So the right figure here shows the results of such an algorithm applied to a set of DECAM data taken with a 4 meter at CTIO. The first dashed line that you see is the detection threshold of a single image. So that goes down to about 23.1 magnitudes. The second dot dashed line that you can see is the theoretically co-added depth, going down to about 10 sigma if we stacked all of the images, and this goes to about 24.5 magnitudes. The completeness of the detected asteroids using the algorithm I just talked about is shown by the blue histogram and is within about 1/4 of a magnitude of the theoretical limit of the data. So taking this approach, applying GPUs, we're pushing the detection threshold about 1.5 magnitudes deeper than the traditional approach for detecting TNOs in single images. And so the power of this is that a single transformation into a likelihood image simplified how we could search for moving sources. And the left figure you can see an example of one of the detected TNOs. And this is from 20 individual postage stamps went into this detection. The co-added image only has a signal to noise of about 15, but the postage stamps that went into the detection of this track have detections at about 3 sigma or less. If we want to take these sorts of techniques and we want to apply them to the LSST survey, even if we're working with just 30 days of observations, this comes with a lot of computational challenges. The longer the baseline for the search, the more area we have to search. The larger the area that we search, the more efficiently we must cache images into the GPU. This is all computationally tractable. Mario Juric estimated that it would take about 10 million GPU hours to co-add about 30 days worth of LSST data. So this is expensive but possible. But more challenging is that the trajectories of the asteroids, even in the outer solar system, are not going to be linear. So while the algorithms that we use assume linearity, the reflex motion of the Earth adds curvature, so the prograde and retrograde motion, and it adds curvature to these tracks. And so for 30 days of data from the LSST, this will create nonlinearities up to about 30 arc seconds. So naively, if we take the approaches that I've talked about before, this would increase the computational resources required by about 60-fold, because we need to be able to search our searches to be within about half a PSF of the true trajectory in order to detect an object. This really makes this project essentially computationally impossible, at least from a cost perspective. But again, if we think about the structure of the data and the model that we're fitting, we can recognize that the complex orbits that we see in the figure on the left, due to the fact that we observe these asteroids in the topocentric space, we're observing from the Earth, so we see the curvature due to the prograde and retrograde motion. If we project into a heliocentric space, reference to the sun, and assume a distance to the asteroid, the orbits become elliptical and they linearize on the sky with curvatures of less than about 1 arc second. And you can see this on the right side of the figure. So we know the position of the Earth. We know the position of the Earth at the time of the observations. So we can correct for this in the searches and reduce the computational complexity of the search by almost 2 orders of magnitude. And the impact of this, just with a single data transformation, is that it simplifies the computational model. It simplifies it sufficiently that TNO searches with the LSST could increase the depth of the detected TNOs from a single image of about 24.7 magnitudes down to about 30 days worth of co-added data. So now we're getting down to about 26.1 magnitudes. This would enable us to detect about 8 times more TNOs than we thought possible, detect minor planets such as Sedna out to about 300 AU, and possibly even probing objects that's originated within the inner Oort cloud. And all of this without taking any additional data. So what I'm trying to show is that if we use our understanding of the physics, moving beyond what has been common today, where we take these data-driven discovery approaches, if we take more of a physics-driven discovery approach, this has a real impact on the computational complexity needed to get to the science. And this is true for classification, and it's true for the other end of the distance scale. For example, using supernova cosmology, where we want to estimate the distances to a sample of type 1a supernovae. So one of the primary limitations on supernova cosmology is accurate typing of the supernovae. Usually we do this by taking a spectrum of the supernova close in time to its explosion. But if we could classify type 1a supernova just from their light curves, we wouldn't need the spectroscopic confirmation. And that would reduce the amount of follow-up spectroscopy using 10-meter class telescopes. And also it would increase the size of the samples of supernovae that we can use in our cosmological studies. We can always get the redshift to the supernova from the host galaxy, and we can do that after the supernova has faded. And because of this, there's been a lot of work on the development of autoencoders and neural networks. And there's been significant advances in how we apply these autoencoders and neural networks to the classification of light curves. And examples of this are shown here with the SuperRain model from Ashley Villar and the collaborators. There are other examples such as the avocado model from Kyle Boone that won the plastic challenge. And together, these different models are achieving about 75% efficiency in identifying type 1a supernovae from samples of transient sources or transient light curves. And this is 75% using not simulated data, but from real data such as PanSTARRS data. Most of these approaches are approaches, as you can see from this example with the Super Ray model, take as input the light curves or fluxes from the supernova, and they learn a model that tries to explain how the light curve varies as a function of supernova type, or as a filter, or as a function of redshift, or as a function of observing time. However, as Carl Boone at Dirac noticed, if we can separate the intrinsic unknowns or the latent variables, for example, the variables that represent the variation in the spectroscopic or the spectral properties of the supernova, we can separate these from the physics that we do know. And the physics we know is the redshift, the filter curves, the host galaxy, the dust or obscuration, and the observing time. If we separate the intrinsic unknowns from the known variables, this reduces the dimensionality of the complexity of the models needed to classify the supernova. So the right-hand side of this figure shows you the latent space of the supernova spectra for different types of transient and variable sources. And this can be represented just by a handful of dimensions or components. So learning just the intrinsic properties of the sources also reduces the need for the training data to be completely balanced or representative. And it also enables us to naturally incorporate additional observations, for example, those taken at different wavelengths. And the performance of this physics-based approach using benchmark data from the Plastic Data Challenge, it's shown on the left-hand side. I'm sorry, I'm being told I'm out of time, but I think this is a 30-minute talk. And so let me just, so the performance of this physics approach using the benchmark data from the Plastic Data Challenge shown on the left. In the orange, we show the Avocado model. And this was the model that won the Plastic Challenge, the Supernova Classification Challenge, winning from about over 1,300 entrants. In the blue, we show the results from this new physics-based approach, and we call this ParsNet. It's important to note that this physics-based approach isn't really an advance in the complexity of the neural network architecture. It comes from more of a careful separation of what we know and what we want to learn. And this figure shows on the left-hand side the completeness of identifying type 1a supernova from a mixed sample of variable sources, where we set the threshold so we'll allow 10% contamination rate. Separating the physics from the intrinsic properties improves the supernova completeness by 10% over at the Avocado approach at a redshift of 0.4. And by the time you get out to a redshift of 1, the improvement is about 50%. If we take a fairer comparison where we don't adopt the data augmentation techniques that were used by Avocado, and we show this in the central figure, then the improvement is substantially better. By a redshift of 0.5, we're about a factor of 2 better than the traditional approaches. If we continue our focus on information, simplicity, and reducing the computational resources, we can consider how these physics-based approaches, opposed to purely data-driven approaches, might impact the analysis frameworks we want to build to deliver the science for the LSST data. One of the questions we're trying to address at UW at the moment is how we should really invest in software for science development. Do we build large scalable infrastructures that try to meet a large swath of the science needs of the community? Such a system would likely take longer to develop. It would be higher in cost, but it has the potential to really multiplex the amount of science that you can extract from these systems. This has not been a particularly successful approach in other fields, such as computational biology, where frameworks have been developed over multiple years, requiring millions of dollars of development. And by the time they were released to the community, the field had really moved on. And so alternatively, perhaps we could be creating simplified structures, running bespoke analyses for specific science questions. This would be naturally more agile, more rapid development, but the applications, the science that would come out would be limited. So one of the questions we've been trying to think about at UW is there a middle ground? And one of the things we're finding is that if we can reduce the size of the training samples, if we can reduce the complexity of the data models, as well as the simplification of how we want to parallelize our approaches to large data sets. For example, can each source or light curve or track be analyzed independently? If we can simplify the models, it opens up our analysis that we want to run to a much broader range of computational tools. And this ranges from the serverless approaches such as CloudNot and LithOps. These essentially take Python functions, containerize them, and allow them to work on cloud services, or whether we use the more traditional parallel analytics frameworks such as Spark and Dask and Ray. And this isn't really to say that you can't run complex workflows on Spark or Dask or Ray, but debugging of these systems is a real challenge, especially when memory usage is high. So instead, if we can keep the analysis simple, if we can keep the memory footprint small, we can work on extending these existing frameworks to meet the needs of the astronomers. An example of this approach is the AXIS, or Astronomy Extensions for Spark, which extends Spark with a data partitioning scheme that's appropriate for sources distributed on the sky. It adds in a sort, merge, join optimization for cross-matching large astronomical catalogs. And it also enables efficient Parquet file access to light curves, accessing the ZTF data. Spark provides a simple interface for writing user-defined functions, integrating Spark with the ZTF light curves with a data structure that maps to the astronomical objects. So rather than working with tables of observations, we can work efficiently directly with an object that corresponds to a light curve. And this allows us to rapidly and efficiently search through ZTF light curves and look for unusual sources. And in this case, I'm going to show you an example where we were searching through 1.5 billion ZTF light curves. And what we wanted to do is to identify unusual objects, counterparts to Boyajian star. So Boyajian star, or Tabby star, is a highly variable and unusual main sequence star. It was found in the Kepler data, and it was actually found many years after the data were actually taken. So using AXIS on Spark, it took about 450 core hours, or about 2 hours of running on a cloud resource in terms of clock time. And it took about 450 core hours to process about 1.5 billion light curves. And it did this to identify periods of dimming within the light curve that looked like the variability that we're finding in Boyajian stars. And these are broad dips in the light curve lasting multiple days. It then took us about 10 hours to save the results to disk, which is a different story. But because the analysis was simple, because it had a small memory footprint, it was easy to run. And this was critical because the science workflow turned out to be very iterative. Identify an unusual set of light curves, correlate with known features or bugs in the processing, filter out the unphysical results, and repeat until the astronomical sources were left. Keeping the memory footprint low meant that we didn't have to spend a large amount of time debugging Spark, which, as many of you know, can become a challenge because you rapidly end up working trying to debug Scala at the bottom end. You can see some of the results of this work on the right-hand side, which shows you some of the 11 Boyajian star counterparts that we actually found in the 1.4 billion light curves. So this is really spending 2 hours of compute time on a cloud resource, but not 2 hours of work to find a 1 in 100 million event. And so as we developed the Boyajian star, what we began to realize that debugging, even though the debugging was limited, having people who knew how to write and who developed the system, having them available to support the work that we did really accelerated the discovery process. And this really isn't restricted to astronomy. In a survey of about 330 PIs at UW, one of the problems that was mentioned was the lack of access to software engineering to build robust and maintainable code. It wasn't access to the actual funds, it was access to the actual engineers to do the work. And so this has actually led to a new initiative that's just started up to support the science for LSST. It's called the LINC Frameworks, which is a program housed at CMU and the University of Washington, supported by the Schmidt Futures Foundation. LINC's goal is to build on what we've learned in developing scalable analysis tools, And initially, we're going to be developing algorithms to support solar system science, time series analysis, and photometric redshift estimation. And our goal is really to use professional software engineering examples, bringing in experienced industry-trained software engineers to develop open source tools. And so as a somewhat of a shameless plug, if you're interested in working on building these tools to make science discoveries with LSST, I'd be very happy to talk to you. So we are actually hiring. So as I know, as I'm coming to the end of my time, let me wrap up by just saying that it's not really the volume of data that's really driving the challenges in astronomy, it's the complexity of the science. So when we spoke with the science collaborations working with Rubin Data, they identified a number of science cases that they wanted to work through in the first year of operation, requiring about 100,000 to 3 million CPU hours. If we could focus on the physics of these questions, we might be able to reduce the computational needs. It's not just really about the hardware. The tools don't always exist, even industry tools that are robust enough to scale to a typical science analysis. And this means that we need to be able to extend these open source packages, whether it's Spark or Dask or Ray, to work with astronomical questions or to address the astronomical questions. Extending existing software, whether it's industry or academic, requires significant software engineering skills and isn't really the job for a typical graduate student. The Access extensions that I talked about earlier in this talk still haven't been integrated into the Smart Master because it takes time and resources to upstream changes into the underlying code base. And so we're still in the position where we're supporting a branch of the code. But I think there's a real opportunity to identify what are the needs in terms of developing and extending the software tools. And can we actually build a roadmap for the science software infrastructure? And can we actually build this across multiple astronomy science experiments and potentially across different scientific fields? And by doing this, we might be able to bring together some of the software engineering support that we need to extend these open source packages and to make them useful for the science that we want to do. And so I'll thank you for your time, and I'm happy to take questions. And if you don't have questions, I'll leave this contact information up if you're interested in working on the Link Frameworks project. Thank you.
Okay, thank you, Andy, for the interesting talk. Any questions from the audience? Okay, there's a couple of questions on Discord. One question by Michelle. She asked, do you have any thoughts about how these techniques can be adapted for real-time classification, which is, of course, what we really need to optimize spectral follow-up?
So I think one of the really interesting aspects about the ParsNet work, the classification of the light curves, is that it appears to work well for early observations of light curves. And it also comes with a probabilistic classification or a probabilistic representation of the light curve itself. So I think we can begin to integrate these sorts of tools. And I believe that Kyle has already integrated ParsNet into one of the alert brokers. I believe it's currently working in Ample, and it's connected through to the ZTF data. So I believe these sorts of techniques that, because you can constrain the complexity of the model or the dimensionality of the model, then you can actually get reasonable fits from a small amount of observations. And so you can do these classifications quite early in terms of the supernova light curves. So I think there's a lot of potential there. And actually, I think it'd be quite interesting to see how well it performs with real observations, with the latest observations coming out of ZTF.
Okay, thank you. The next question was from William. He asked, my worry always is that the great Spark examples are single user examples, but how does it work for 5K astronomers? Do each need a Spark cluster, or perhaps we go back to the shared resource model, apply for time?
That is a really great question. And I think I noted and I didn't really get a chance to talk about this, but one of the real challenges is Spark and many of these tools don't really work in a multi-tenancy environment. They're assuming that you essentially have your own Spark cluster accessible to each individual astronomer. So we're not really sharing resources. I think this is something that we need to work on. And then I think this is one of the clear examples about where if we can bring software engineering expertise within astronomy, we can potentially adapt and modify these techniques, or these analysis frameworks, whether it's Spark or whether it's Ray or whether it's DAS. But to do that requires significant amounts of software engineering support. And this is why I think this is the place where if we can identify what are the clear needs for each of these platforms, we might be able to bring some of the resources together to be able to actually bring engineering teams to actually address some of these questions.
Okay, I think we are out of time now. There's a second question from Michelle. If you can address that on Discord, that would be appreciated.
I'm very happy to do that. Thanks very much.
Okay, thank you. Can we thank the speaker one more time? Okay, the second speaker of the session is Spesihle Makhathini from Wits University. He will be presenting about STIMela 2.0, containerization and workflow management for data pipelines. The floor is yours, Spe.
Good morning, everyone. I'm Spesihle, as Athanasis has just said, and I'm going to be just talking about STIMela and some of the improvements we have made over the last couple of months. So just to give you some context about how STIMela came to be, it was about 6 years ago when I started my PhD. I was given a few tasks by Oleg, who was my supervisor, and one of those tasks was to improve on his record-breaking dynamic range image of 5 million to 1. The second task was to do simulations to optimize the SKA1 mid layout. And the third task was to basically use, again, simulations to quantify how direction-dependent effects would affect a survey if you were stacking many images from different observations. And what I quickly found, and I had like multiple platforms to do this, it was the South African CHPC. The next resource was the Google Cloud Platform, servers at Rhodes, and AWS. And what was the issue was that I would be able to make the pipeline maybe to work on one system, but then when I had to move it to a different system, it would just be a mess. Some libraries would be outdated, making things to work will be very, very difficult. And just out of sheer frustration, we developed this tool. And yeah, that's just the background. So we found a few problems with radio astronomy software. And the first one was that the software is often written by astronomers, PhD students, postdocs, and not by software developers, and it's not very stable. It's very difficult to build, it's not well documented, hard to install. And if you want to install more than one package on the same system, good luck to you. Basically, we had Casa, which can do most things. However, Casa does not play well with other things, so it's very rigid. And if you are using Casa, you basically have to stick to Casa. So this was not a very good environment, I found. But so this is from 2014. Some of these things may have changed, but let's go on. So basically, the goal for any pipeline was just, I'm going to make the pipeline work on my system, work on wherever I'm doing it, and everything else was not really considered. Okay, so when I was basically coming up with STIMela, so basically the main principles were I wanted to be able to do reproducible reductions. I wanted it to be simple and to be portable. So basically, given a given data set, I want to be able to take my pipeline, which is some sort of script, give it to another person, and given the same data and similar resources, they should be able to reproduce what I have done without fiddling too much with system admin duties. And simplicity, it must be easy to build, easy to understand, so that like someone who is not an expert can just read your pipeline and sort of get an idea of what's going on and make modifications if needed. And for portability, you want to minimize the dependence on the system, on the OS, on libraries, on the system, and so on. And it must be easy to share, or even if you have your scripts on GitHub, you must be able just to share them with your collaborators, and they must be able to use them as they want and run them on their own system and so on. So this basically, in this way, we would aid easier collaborations. So just to summarize, we want a well-documented and flexible framework, basically, that will allow us to create pipelines which are robust, which are reproducible, and which produce quality data products. Okay. But as I just said now about quality, is that reliable is not good enough. So you may have a robust pipeline, but it may produce like mediocre science results. So what we also need to have is the ability to keep up with novel and cutting edge tools in the science. So we also want the flexibility to plug and play new tools as they're being developed, so that we keep up with whatever is current. So this is just like what happened with the first task that I was given. So at the top, this is Oleg's image. I should use this actually. So this is Oleg's 5 million to 1 dynamic range image. I think this was around 2013 when this was produced. It's VLA data of 3C147. So it was a beautiful image, a lot of press about it. So yeah, it was a good time, and this is when almost I came into the field. And my duty was to try to improve on this. We had new data from the VLA, and yeah. And basically when we had STIMELA, I think after like 6 months or so, we were able already to do much better, but then I only submitted my PhD much later. But we were able to, using this new framework, to produce a better image. And this image was produced using Cubicle at the time, which was still very, very new, as well as DDFacet, which was also very, very new. But like because of the ease of being able to plug and play new tools, we were able to do this quite easily. Okay, so yeah, let me just go to do that. And basically, and the problem is now, how do we do this more consistently? So these are just like 6 points that I think are important whenever trying to build either a pipeline or a system for creating pipeline like STIMELA. So version control and issue tracking is very important, as I'm sure every one of us would agree here. And for doing that, we have GitHub, GitLab, SourceForge, SVN. The latter two may be outdated now, but you know, whatever you want to use. You need to have good documentation. I know it can be very boring and laborious, but it's very good if you want people to be able to use your software and be able to troubleshoot and figure out if things go wrong. Another thing is packaging. Packaging is also very important. You must make sure that your people are able to access your tools, again, without too much problem. So just like a simple pip install or apt-get install is very useful. Okay, continuous integration, make sure that you're testing your software regularly, and that if there are any bugs, you're able to catch them quickly before other people face them. Isolation and portability, we use Docker for this, because as I said, installing more than one of these tools on one system can be very difficult. So what we do is we isolate everything and then release it as different packages. Okay, and we also try to go for simplicity, and for this you can use Python, Jupyter, YAML, or any other system. So this is the design of STIMELA. You can have any tool that you want. Usually we get these tools from either PyPI or Ken Suite, and then we wrap them up in containers, or you can put it in a venv now, or you don't have to have any wrapper. You have some Python backend, which will give you access to all the tools in a simplified, unified interface. This is where you do your scripting. And here I just have two simple examples. It's one example using both the YAML and the Python interface. So this is basically a very fictitious self-cal loop where you calibrate and then you image. So this is just how you do it in YAML and how you do it in Python. And running it in Python, it's StimulaExec, and then Stimula run in Python, and then StimulaExec for YAML. Okay, and so this is not just me. It's a sort of a big group now. It started out as just me, and then Ben came along to work with, and then really has done, I think, the most work behind me. So, and of course, there's other people also who are working on this, and yeah, it's not just me. I think, yeah, as I say, it takes a large group, not really too large, but it takes a group of people to actually create good software that is also useful and usable by other people. And one of the things which I appreciate about Stimula is that it makes the barrier to entry for people who are just coming into the field, as I was 6 years ago. It makes it much easier for people just to start and hit the ground running without having to worry about many of the things that I had to worry about 6 years ago. So there have been multiple students now who can just start their project without having to worry about installing things and making sure it works on their system and so on. So it's just easier for people just to focus on their science and focus on optimizing their pipelines. Okay, and there are two pipelines. I think they are probably the most used pipelines for Meerkat data, and they are both based on Stimula. The first one is Caracal, and the other one is FEMeerkat. Caracal, this is the Caracal team here, including Ben. But Ben, again, out of being frustrated with the team and things going slowly, ventured out and created FEMeerkat because his PhD was due soon. So there's also FEMeerkat. But basically, they are quite similar tools. And then I think Ben is going back to Caracal now that he's done what he needed to do with FEMeerkat. But it's still a very useful tool either way. And this is like some nice images from FEMeerkat. The top one shows direction-independent calibration that Ben has done, basically through Stimula and FEMeerkat. And I think some tools that he had to write particularly for this, but once he wrote the tool, it was easy just to plug it into his pipeline because Stimula allows you an easy way to do this as well. And just a similar thing on the bottom image. These are some of the cool results we have had from the Caracal pipeline. The top image, the blue top image, was a discovery of these collimated synchrotron emission by Mpati. She's sitting at the back there. Again, we used the Caracal pipeline. Like, it was just easy to get this image. It didn't really take much effort. But now we are putting even more effort, especially Landman, to study this more, to image it better, because it's a very complicated field. And if you want to get high dynamic range imaging of this, you have to be very careful. And this is what Landman is doing. Please see his poster. And also, this is a nice image from early Meerkat data of Phonex A. And the image on the left is basically these are Meerkat images of the GW170817. This was the first detected measure of a neutron binary system, and I used Caracal basically to do the Meerkat follow-up of the radio afterglow. And there's also student projects which use the Caracal pipeline. Again, students can get their data. Especially, there was a call for students, and they were prioritized in the first open time for Meerkat. And many were able to use this Caracal pipeline to go through their data, and it just made things easier for them. I think everyone here has now graduated or is in the process of graduating, so that's pretty good. A few words about distribution, but I'm not really going to say much here. So Stimula itself does not really concern itself with optimizing. Does not concern itself with optimizing things too much. Basically, it's a very high-level tool, so we also optimize things at the highest level. So I'm not really going to go too much into this. And these are just the conclusions, stuff that I've already said. It's portable, usable, easier barrier to entry for people who are coming in. If you want to try something quickly, this is basically what you want to do. And then also, if you want to build a robust pipeline, this is definitely the tool for you. So thank you for your time.
I see we have a question by Oleg.
Yeah, thanks. I've got a question to tee you up with. We've heard about other workflow management frameworks at this conference. How does this compare to CWL? How does this relate to CWL? And also you showed parallelization. Can we have loops? Can we have conditionals?
Yeah, exactly. So actually, with StimL, I think in the early stages, I tried to adopt CWL, but CWL is a very rigid standard, and it was very hard to make very simple things work. So the effort, and I even at some point had a compiler, which will basically, you could write some Python code or YAML code, and it would compile to CWL. But this I found to be not the best way to go. So CWL is very good, but I think they have domain-specific things to radio astronomy that they just don't cater for. So this was a better way. And yes, you can do loops and conditionals in StimL, which you cannot do in CWL.
Cool, thanks.
Cool.
Let's thank the speaker again for the interesting talk. Okay. The last speaker of the session is Mathieu Civilat from Observatory de Paris. He will present about fair high-level data for Cherenkov astronomy.
Yes, thank you. Thank you for having me. The slides I will present received a large input from the ESCAPE project partners. And I'm also part of CTA, which gives some inputs to ESCAPE as well as a very serious use case. And Catherine and Matthias are coordinating this participation to ESCAPE. I also received many input from the IVOA, the Virtual Observatory Alliance, and my local data center in Paris. So to explain a bit the ESCAPE project, I just give the acronyms here. It's Science Cluster for Astronomy and Particle Physics Facilities in Europe, so the research infrastructures. See that there are several packages in ESCAPE, the virtual observatory part, how to put data in a data lake, how to plug this with software and services, and combine all this in a science analysis platform. And this is really in the idea of an European open science cloud. So now the context of data generation, particularly for large observatories such as CTA, is that you have a large consortium building a very massive instrument. Data acquisition is made with high rate of data, large data, that is put in different data centers that can be in several locations. Then you have a system for archiving and dissemination. And finally, the end user gets this data. But then to do the work and really have some results, there is more than the user needs than the data. The data product generation is too obscure to the end user. So when we are talking about Cherenkov data in particular, I give you here the cycle of this data, different data levels from the raw images, calibrate it, then reconstruction of events. And what we are talking about here are a gamma-like event. So this data level 3 is a list of tera electron volt, very high energy gamma rays, candidate photons, for which we get the coordinate, the time, and the energy. It's very low count statistic. We don't have that many photons, and it's a high background. Then this is publicly available, and well, this can be reduced and adjusted for science purposes. Here are the final results that you may want in a publication. So how to make all this data fair? I give a link here to the talk on Monday and to Go Fair. Those 4 topics of the FAIR principle received some solutions from our part to match with the Cherenkov data. And first, to be really findable, we use the virtual observatory standards as expected, because it's tailored to make data findable. We have a set of public data from the HESS experiment, so a Cherenkov telescope in Namibia, for which we developed a VO, Virtual Observatory OPS-TAP service. So OPS is for the use of the observation data model core components that has been adapted to Cherenkov data. And TAP is for the stable access protocol, also developed by IVOA. And this service is registered to the VO registry, which makes it fully findable by several tools, even if you don't know that the data exists. So here I have examples of TAP handle, where you put HESS and you have a proposed result, which is our service. Here I downloaded the background image in tera electron volt data and Fermi data, and overplotted in green all the data from this public data release. And here we use Topcat to do a query directly on the table. So obtaining the data is another issue. Now that we selected and found the data, and we base this access to the access URL field of the OPSCORE data model. And here I show the direct download of a FITS file. So I have my OPSCORE records, and this access URL with a simple click in Aladdin will put all the gamma ray photons that have been detected during this run. We are also testing and implementing a data link service so that we don't get only the photons, but also the associated calibration data. And we are thinking about the service that would collect the data plus the calibration to feed the science analysis tools. There is the question of access rights. And for this, we anticipate the need for permission, a proprietary period for principal investigators. And there is this IAM Escape service that we intend to plug with the system. Now, to make really the data fully interoperable and more widely than what is allowed by the virtual observatory standards, there is a community standard within the Cherenkov astronomy shared with different facilities to define a common data level 3 data formats for gamma ray astronomy based on FITS. And this is completed with a dedicated Python package for gamma ray astronomy. And all those show the community effort to discuss and find global solutions together. So work and discussion are in progress, but there are several formats that are proposed, and it's a prototype for CTA. It's already used by HESS and by several current instruments that there are already publications based on this data and data model. And GammaPy is an open source Python package, will be used as a core library for the science tools of CTA, already in use. And I give a link here to the recently proposed FAIR principle for research software, not the data, but the software itself. And GammaPy is a kind of project that tries to match most of the FAIR principles for research software. There is also the ESCAPE OSSR, an open access repository to share scientific data, and GammaPy is part of this project within ESCAPE to make the software, as well as the data, as we have seen, available to the public and to all the community. Now we have FAI, how to become fair. As we have seen, first we use the virtual observatory standard. We have to discuss and define community standard, and this is still work in progress. But there are technical solutions to those items. Reusability is a bit more subtle. It's based on the quality and the reliability, trustworthiness of the products. And this is not just a technical solution that you are given. It's a context, a metadata that explain how to use the data and how the data was prepared. If you ask question, what calibration was applied? well, you need to find the processing and where the calibration was applied to actually match and check that it's a good calibration. What tools were used and how they were used. What assumptions were made during the data preparation. And in particular, with time, this key information may disappear. You may have written it down somewhere, but well, with time, sustainability is not met. So one of the key answers to this is the recording of provenance information. And we need for this the origin, the trace, and the detailed manipulation of what happened. This needs to be structured. It's not just on the spot that you want the raw data and the final product. You also want to have a structured path that explains you each step that was taken during the data manipulations. And we need to keep it and link it to the data. This is why we developed recently an IVOA provenance standard data model as a recommendation. And I present here the glossary of concepts that we use when talking about provenance. And those concepts are used on the internet, proposed by the World Wide Web Consortium, that you have a chain of activities and entities. Entities are used and generated by activities. Activities can communicate or send information to other activities. Entity can be derived. All this vocabulary is the basic vocabulary we use when you are talking about the origin, the path of the data, what happened to the data. It's associated to an agent or attributed to an agent if it's an entity. Now the IVOA provenance data model developed help to fill this basic structure or graph or the backbone of the provenance with useful information. And I'm thinking about what is the activity that really happened. See here, we have a tree of activities, entity, activity, entity, activity, entity. There is this backbone here. And in orange, there is a description of this activity, really what happened. And you get here some description and some links to understand what happened during this activity. You also have here the configuration parameter that's been sent to this activity to really know how it was performed, what happened during the algorithm, and how it was configured. Also, the entity is explained by an entity description so that you can access it and distribute it. So when we talk about provenance, there are several concepts that come in mind and that are a bit different. I presented here a graph for the full provenance, really this graph that traces activities and entities up to the raw data. And this information cannot be hosted in an entity itself. It should be stored in a central database or separate files. We are also thinking when we talk about provenance about this key information that we need to use. And for CTA, it would be, well, this event, is it a gamma ray event? Is it something else? What was the telescope configuration? The sky condition, the reconstruction method that was used. All this is somewhere in the full provenance, but is also attached to an entity so that it's directly used to process this entity. And we are proposing the development of the last step provenance that would be really some keywords embedded into an entity about the last activities. So by then, using this with links to previous entities, last entities, you could reconstruct the full provenance step by step, just by having this last step provenance stored in entities. I give you links here about the discussion we had at ADAS and within an ESCAPE workshop, and I will be talking about this during the IVOA meeting next week. So in a word, what scientists generally have in mind is that, well, you do some process and then you store some data in the header, some metadata, and it's embedded and people will know about it. But we need a more advanced provenance management, and we include capture inside the process, really at each action. This is stored in a central database, and this can be visualized by standard protocols and tools developed for this. I give here just a few examples. and a link to a more detailed presentation of those. So now all this can lead to the development of a full science portal for fair chunk of data. So making fair data requires discussion, anticipation. This VO compliance is a requirement. It is written as a requirement for CTA, for example, and other infrastructure facilities in ESCAPE. We need to capture this relevant metadata along the process. So this science portal would offer an advanced search dedicated to chunk of data, some data preview and selection, and then an online processing with provenance tracing. This is what we expect associated with user management and space. We have test implementation. I give short links here and snapshots. And I thank you for your attention. I have to say just one word that we also are looking for a postdoc to work on the fair chunk of data in general. And I will be posting this announce on Discord. Thanks for your attention.
Thank you for the talk. Any questions from the audience? Okay, I'll have a quick question. So since you mentioned that the data products are accessible, so I wanted to know if they come with like some diagnostics to see how the uncertainties in making the products.
Yeah, maybe you are talking about some flags or warnings that could make the data, well, more or less precise.
Yeah, so
quality factors, quality.
Yeah, exactly. Yes.
Plan. This is of course done, and there is a full process. So calibration is a bit complex with chunk of data. You have first a rough calibration that is applied, and several days before you can compute a real full calibration. So you have this flag of what level of calibration was applied, which makes the data different. And I'm also thinking that in the provenance data model, we dedicated a label quality to some entities. So at some test activities, you can generate those quality entities that would help the user determine if the data is sufficiently good quality for it.
Okay, thank you so much. I don't see any questions on Discord. So let's thank the speaker one more time. So there will be a quick poster session on display now.
I am Gilles. I present a poster which compares two worlds, open data network in the edition context and IVRA framework. With the rise of open data, concepts emerge and certification as the Quartus seal becomes essential. The both are required to develop fair workflow and needs data expertise. For instance, a criteria in the Quartus seal as a data center to ensure sufficient metadata for end users. IVRA data models go in the same direction. About fair concept, the interoperability means more an interconnected network according to the RDA FAIR principles, whereas IVRA develop a very high concept of data reuse. In a second step, I focus the poster on the search aspect. DOI architecture and IVRA registries provide both metadata, including provenance. They have particularities. DOI provide a rich semantic to link resources, including the role existing between them. The IVRA registries provide metadata access to be machine reusable. Both aspects are important and continue to be implemented in the Bezier catalog service.
Hi everybody, we are the team that makes ASCAPsoft, the radio astronomy software for the calibration and imaging for ASCAP project, which is based in CSIRO in Australia. You might have heard a number of surface science projects that use ASCAP. Parts of the software that are not ASCAP specific have been released as an open source software called YandaSoft. Recently, we released version 1.3. In this poster, you can see a glimpse of behind-the-scene process that produces YandaSoft. We use Gitflow to manage multiple concurrent development of various functionalities. As build system, we use CMake, structured in a way that helps us resolve complex dependencies and release the software on regular basis. We rely on Docker and Singularity containers to simplify deployment to users, whether they are using laptop or HPC. Please check out our website and follow us on Twitter. Thanks.
Okay, thank you. And then one more announcement is that there's going to be a conference photo on GatherTown. So for those who didn't have an opportunity, this is your time to get one. So this is going to happen now, I think. So if anyone, if everyone can go to GatherTown. And this is the end of the session. Can we thank all the speakers one more time? So over to GatherTown now. Thank you.
Right, welcome back everyone for this final short session ahead of South African lunch. Oleg reminded me before the session that the session chairs should introduce themselves as well. My name is Roger Dean. I'm from the University of the Witwatersrand in Johannesburg, South Africa. Right, so we have 4 talks, 15 minutes each, and kicking us off is Jesus Salgado talking about designing the SKA Regional Center Network.
Salgado, I'm going to talk today. For sure you have heard several times during this meeting about the SKA Observatory that is going to have an unprecedented sensitivity and also going to produce an amount of data, scientific data, and it will require some computational resources at the level of big data. So it's a technological challenge, not only a great observatory. The first phase of the SKA will have 2 locations, SKA Low in Australia, that is going to be composed by 130,000 antennas, producing a data rate of around 7 terabits per second. If you see the image of the expectation of the future SKA Low images with the current resolution we have in radio observatories, you can see there's going to be a very prominent improvement. The second location is here in South Africa, SKA 1 Mid, and it's going to be composed by around 200 dishes, and it's going to produce a data transfer rate of 9 terabits per second. And also you compare the images, the expectation of the images with the current level of resolution, you can see that scientifically it's going to be a major challenge and a major improvement. If we only analyze the data flow, to analyze the data sharing, there are going to be two three streams of 7 terabits per second and 9 terabits per second, more or less, that are going to be reduced in the central signal processors to 5 terabits per second, more or less. And this raw data is going to be reduced and converted in science data into the SDP, the science data processors, producing more or less 600 petabytes per year. That is going to be shared to the user community. This is going to be done through the SKA regional centers, also called SRCs. And the SRCs is basically a set of nodes all across the planet where we are going to distribute the SKA data. So in this way, we share the resources of exposing the SKA data. That is quite considerable. That also implies that we need to have a dedicated fiber links between the different nodes to ensure that this movement is possible. That produce what they call the SRCnet. At the end, what we have is a data lake that with a lot of astronomical data ready for access. And if you know about data lakes, you know that there are pros and cons. The pros, for some, is that you have all the data available, so you can do whatever you want with the data. The users can enter in the data lake and use it. The cons is that there is no data processing integrated. That implies that you are working with unstructured data analysis, and the analysis could be complex at this scale. Also, we can face latency problems because the data you want to analyze could be in a remote SRC location. And also the third important point that I want to talk about now is that you don't have data domains identified. If you put the concept of data domains to a data lake, you have a data mesh. A data mesh could be composed of data types or could be related to the scientific data domains. That basically is that we know that when you are using the data, you don't use it blindly. You're using a third-time data domain that implies that you know the operations you want to run on the software, on the data software, producing analytics data in return. So basically, is you can focus the use of the users to a certain data domain. One concept that is inside is the domain data as a product. That implies that the domain data product is not only the files, but also the software that is able to analyze it. you have the code, and also you have to as one dependency, and a second dependency you have the hardware that you need to run and the infrastructure you need in order to execute the code. That could be specific of the use case you are using with the domain. The third axis is what they call the polyglot data metadata, that are the different formats that you can have for the data or for the metadata in return. So as an example, we have here in a sketch of what you have in data cubes visualization data domain. Basically, the operation is going to invoke a visualizer that could need to slice a data cube per energy. That implies that if you haven't defined the data domain product, you know that how to create a layer for one data cube is a certain code that is close to the cube and executable in a certain infrastructure, and is going to produce in return a slice. So you know the operation and you know the return. So you are defining data domain. And how it works in general, if you have a data cube produced in Australia, in the future for SKA, and you move this data cube to the SRC in Canada, a user could enter into the SRC node in South Africa and try to invoke the visualization of this data cube. So the first thing that data cube is going to produce, is going to invoke, is the slice data cube energy to visualize a slice. You can be tempted to move the data cube from Canada to Australia to work locally, but it's quite inefficient in the case of big data cubes. But if you define data cube as a domain data product, that implies that you know that whenever you have moved the cube to Canada, you also have ensured that dependency, that is the code needed to do slices, has been also moved to Canada. That implies the visualizer is able to invoke the code remotely and only moving the return result, that is basically the slice. In the case of visualization of data cubes, it's something that many people are already testing, so putting different servers all across the planet, for example, for Carta, whatever. But the idea is to define a way that this is done for all the kind of data. So basically, the data management system is able to move the data and the code efficiently, and is going to be defined by the data domain experts. So basically, the domain experts are going to define what is the code needed to understand and to execute this data domain. We are talking now not only the SRCs as data locations, but also as software entities. We define now that any SRC, all the SRCs, need to implement what they call a blueprint. The blueprint is a set of capabilities, basic capabilities that have to be implemented in all the SRCs, going from data discovery, science-enabling applications, distributed data computing, visualization, interoperability, all the basic needs. And in the core of everything, you have the data management system that is responsible of moving data from the different SRC locations, also from the original antennas, I would say, to the net. So in order to define this blueprint, first we have created several working groups, experts in different areas that could impact the SRC blueprint definition, from the architecture itself, from the data logistics, operations, the computing, science archives, compute working groups in order to define the computing resources. And also one important thing is the science user engagement, basically to extract from the community user stories that you would like, the community would like to be implemented inside the SRCnet. Then we are already defining the functional decomposition of different aspects of the blueprint. And also we are defining the different modules and the interconnection between them in order to implement this blueprint. This software is going to be developed collaborative between all the SRCnet members. We expect to have certain heterogeneity in the definition of the capability of SRCs, depending on the expertise of the SRCs. That could imply expertise in data domains or scientific domains that could extend in some way this blueprint. So the main thing is going to be the blueprint that can be extended. And also there are going to be links between the different nodes that are going to use FAIR or video protocols whenever applicable. Everything, the blueprints all around the net, the data, the sender capabilities, the protocols, the APIs, everything is going to be what we call the SRC net. There are certain rules to define efficiently this data management, this SRC blueprint. In the case of data management system, we need to prevent or avoid unnecessary duplications or transfer, because what is very expensive, first, and secondly, it's going to be inefficient. So we have to create a system that is able to find the best way to move the data. But also we need to have good user experience. That implies that maybe popular products are going to have different replicas in different SRCs, monitoring the use of the data by the users, and also with the concept of data mesh. We're exploring data management system able to handle exabytes. There are not too many. We're starting working with Rusio for the third. And also another principle that we should be able to use collaborative work. Basically, the users should be able to share resources in the net, share workflows in the net. So they should be able to work in the net as much as possible, because downloading the data is probably not an option in several cases. And also very important is you should be able to reproduce the results. So when you have a paper in the future of SK data, you should be able to take the workflow and reproduce locally. Also, the protocols, as said before, should reduce your protocols when applicable, or use FAIR protocols, because as said, all the different models are going to be implemented globally by different teams. And it's important to give credit to the people working in the models, because all the resources, not only the resources of the repositories, network, or whatever, the infrastructure, also the people, the engineering teams to develop the software are going to be a pool of resources from the SRCs. Basically, all the people the SRCs are going to provide engineering support. We are going to create agile groups across the planet with different time zones, create a consolidated network of people working in the same software. We are already working in the definition of the SRC net models, and we expect to have a full functionality, a full capacity for 2030. And that's all. Thank you for your attention.
Thank you very much, Jesus. We have one question in the chat here from Rahim Lakhu. What is the plan to handle network connection errors? For example, if the network connection to SRCs goes down for a day, there may be a backlog of up to 1.7 petabytes for transfer.
One thing that is important is to be able to extract all the data from the original antennas, we'll say, to the SDP to the SRC. So one thing that is good is that we have SRCs also located very close to the antennas location. We are going to have one in South Africa, another one in Australia. So one way is at least to put the data outside to a cache, and then the SRC network, whenever it is available, do them in the data management. So the most important thing is to extract the data from the operational point of view from antennas to the SRC net, although it could go to the closest SRC in this case.
Thanks. Any other questions in the room? I'll ask one on the number of SRCs is there. Would you like to comment on that, at least in the first instance?
There is no agreement yet of how many we are going to have. We know that there are some of them that are, for example, we're going to have one in Australia, South Africa, Europe, Canada, China, probably India and Korea. They are working to have one, but we need to have the formal agreement because there is a formal enter into the SRC net with certain rules, basically ensuring the hardware, ensuring the resources, and this has to be a formal agreement.
Okay, great. Thank you very much. We've hit the quarter hour, but there is at least one other question coming through, which defer to the chat. But let's thank Jesus again. Right, from distributing data across the world to moving astronomical data into planetaria around the world. Our next talk is Venustiano Aguilar, talking about a tool to explore astronomical databases and transform data into planetarium formats.
Hello, my name is Venustiano Swancat Aguilar, and I will talk about the tool we are developing at the University of Groningen. This tool can be used to explore astronomical databases and transform data into planetarium formats. I work with Rhys Williams, Adri Matlener, Edwin Valentine, and Josh Rording. In Groningen, we have a 3D dome facility in which master students give shows to the general public. And occasionally, astronomical staff give presentations to the general public as well. In most of these presentations, the latest data releases from Virtual Observatory are not included. And this is mainly because downloading and transforming the data into planetarium formats is a time-consuming process. So we can download data by using web portals. So in these web portals, we have to select the tables and columns that we require. And then we have to download it manually. We can download the data in a programmatic way by using application program interfaces such as AstroQuery, CastJobs, and PyVO. We have to create a script for each dataset we would like to download. And then once we have our dataset, we have to transform the data into appropriate planetarium formats. So we have to transform our raw data into X, Y, and Z variables, or color and velocities and radial velocities. So to do this, we have to create a Python script or an R script. And this process is a time-consuming process. So the main goal of our tool is to make it easy for staff and students to include virtual observatory data in their presentations. We want to exploit the virtual observatory archives because the data is there and we should use it in our presentations. So in short, we would like to accelerate the process of bringing data into DOM. So our tool has 4 main modules. It has the graphical user interface. It has a controller which can connect to the different astronomical catalogs and download the data. Then we have a planetarium format module which converts the data into spec or binary files. Then we have a module to store the data into a database. And this module or model contains 2 main entities. The main entity, one of the main entities is the query entity, which stores information about the ADQL code used to download data, the number of rows, the runtime, and the file name in which the data was stored. Then we would like to store information about the conversion process. So we want to store information about the file name, runtime, and variables used to transform the data. Then we have created a graphical user interface. And here I would like to present the running software. So this software allows the user to select different astronomical catalogs. So once the catalog is selected, the tables are displayed in this panel.
And then we can select the tables, and we can select the variables or columns that are in the table. So when we select the variables, this panel is populated with the selected variables, and we can remove them if we don't need them by pushing this button. Then we can also add conditions across tables, and we can generate the ADQL code more or less automatically. Then this is the most important panel, because here we have the ADQL code, which can be modified by the user and can be submitted. For this presentation, I will use a previously saved query. And so here I am using a query that downloads data from the Gaia catalog and downloads variables that can be converted into a spec file. And the data is stored in this file, in this CSV file, Gaia DR3 1K CSV. Then this file can be converted into a spec file by clicking in the Convert tab. So to create a spec file, we need a number of variables like X, Y, and Z, color, absolute magnitude, velocities, and speed. So to estimate X, Y, and Z, we need variables like array, dec, parallax, distance, or redshift. So the software looks for these variables in the CSV file and try to find the best match. So if the variable selected is not correct, then the user can select one from the list of variables that are in the CSV file. So this one, in this case, was correct. Then once the user has verified that all the variables are correct, then the spec file can be generated and saved it in a file. So in this case, I will create Gaia test and then save it. And then we have some details about the file and information about the transformation process. And we can save it. The results, we can see the results in this terminal or in the terminal. So the file has been created. And we have created a number of tests and queries, and a summary is presented in this table. We have created or downloaded files from different catalogs like Kits, SDSS, and Gaia. Each of these downloads contain a number of rows. The smallest one is this one with 500,000 rows and a file size of 30 megabytes. And the time to download this data is about half a minute. The longest query is one performed to the SDSS catalog containing about 185 million rows. The file size was about 11.5 gigabytes, and it took about 16 hours to download the data. Once the data has been downloaded, we have to visualize the data in a Planetarium software. This is a pipeline that can be used. So first, the CSV file and the spec file can be generated using our tool. Then the spec file by itself can be displayed into
the open space planetarium software or SkyScan planetary software. However, visualizing spec files is a slow process as compared to visualizing binary or octree binary files. So it is recommended to convert the spec files in these formats. Further information can be found in this link. So we have created some visualizations like this one. This is a screenshot containing about 13 million objects from SDSS. And this is another screenshot from OpenSpace containing a section of visualization. And here the objects are not further away than or farther away than 1,000 parsecs. Then we have some conclusions. Well, we have created a tool that can query different astronomical catalogs without much effort. We can store the history and metadata of the queries. We can transform astronomical data into suitable spec file formats to be used in planetarium. Downloading huge amounts of data can still be time consuming. So we think we are accelerating the process of bringing data into DOM. We have some future work. The first one is to prepare the first release. We would like to support concurrent downloads. We would like to improve the robustness of the software. And we want to support different input and output file types. And we also want to support or be able to download data from other catalogs, such as Euclid and Simbad. And we want to increase the processing speed by using file formats other than CSV files. So this was my presentation. If you have any questions, I will be happy to answer them.
Thank you very much. I see some questions coming through in the chat. Maybe just a quick one while we wait for those. Of course, I imagine you have the capability to load up a spectral cube, a data cube, in addition to the catalogs that you've been talking about.
Sorry, could you repeat the question again, please? Because I didn't hear correctly.
Sure. Of course, I imagine you are able to convert spectral data cubes in addition to just catalogs in FITS format as you've described.
Well, it might be possible, but we haven't tested that. But however, yeah, we would like to download some data cubes from Euclid, but we haven't done that so far. That will be very, very good indeed.
Great, thanks. The next question is: there are planetarium software dealing directly with IVOA HIPS format. Do you consider using this format as well?
Yes, we are considering using or supporting different file formats. For now, we just have worked with spec files, but the binary files and FITS files will be included as well. But they are not yet in the software.
Okay, great. All right, I don't see any more questions, but we're at the half hour, so thank you very much for your talk. Okay, next up we have Brent Mizalski talking about Data Central Data Aggregation Service. Brent, you're up.
Right, can you hear me?
Yes.
Yes. Great. Thanks for the opportunity to speak to you today about Data Central's data aggregation service. The project was motivated by discussions with my colleagues about the FRB candidate requirements. So data aggregation in astronomy involves finding all data that you have available online for a given sky position and radius, for example, images and catalogs. And the Crafts survey team are doing a survey for FRBs with the ASCAP array in Australia, and they have a large uncertainty in target position that they want to investigate. Is there a host galaxy there? Is there a redshift in the literature? So there are several mature and powerful data platforms available to look for information online, Vizier, CDS Portal, and various others. However, checking each platform can be quite time consuming and error prone, especially if you have a large target list. So to fill this gap, we've developed the Data Aggregation Service, which is a web application that simultaneously queries multiple online data services. Query results are displayed in the browser and may be exported to TopCat or Aladdin via WebSAM, and you can download the catalogs in various formats too. We use Aladdin Lite to provide interactive visualization of images and catalogs together. And we convert HIPS, FITS to HIPS format on the fly for display in Aladdin Lite. The application takes in ArrayDec, field of view, and an error radius, which represents the uncertainty. And then underneath the service queries a whole range of different services. We have a number of innovative features that we have developed since refactoring the application. We had an earlier version in May this year, but now we've designed it to be much faster using asynchronous technologies. Here's a view of the application itself. On the left, you see Aladdin Lite, which can be made bigger and shows you the images and catalogs. The catalogs at the top are displayed in tabs, and you can toggle them on and off. You can, with your mouse over, identify where a given entry in a table is in the image. And you can also load Vizier tables on demand. There's a Sinbad name resolver to go to new targets, and images are shown at the bottom, for example, from SIA services. And we currently have a beta version online. The structure of the application is an ASCII application consisting of, that is served up by Uvicorn, which is a fast ASCII server. And the application consists of two main components, a Python Socket.io server that enables real-time bidirectional event-based communication between the Python backend and the web browser. And the Python backend is, we use Starlet, which is an ASCII web framework that has a range of features, Ginger 2 templates, WebSockets, asynchronous background tasks, and so on. We have several dependencies that go with the application. I've already spoken about some. We use a wide range of IVOA, DAO services, various API endpoints, Vizier, in particular the ASU interface, a whole bunch of asynchronous Python packages, and so on. So to do the simultaneous queries of multiple services, we have asynchronous functions launched as background tasks. And these tasks may in turn spawn other background tasks, downloading multiple images, for example, or launching more complex pipelines. Task results are sent to the browser via WebSocket messages. For example, when a download is done, a message will be sent. And that message will contain data that was retrieved from the service or an image location on disk. The browser is listening for the messages that are on a particular namespace, and the results are added to the page when they're received. VO table and ASCII results are cached using Redis, and converted to Pandas data frames internally for filtering and so on. FITS files are converted to HIPS format using Aladdin and are cached on disk with their location also cached. So I'll go through some of the highlighted features. This shows one of the FRBs from the ASCAP craft survey team. We have a custom Redshift aggregator that queries Visio for UCDs with source.redshift. And we provide a RADEC catalog with Redshift and the columns that were extracted for the Redshift from that catalog that we found. We have multi-wavelength HIPS overlays. At the moment, just a few radio surveys. So for example, this is from the ASCAP RACS survey. And this is just, displaying on top of a Gemini mosaic that we produce. We check if targets have coverage in the survey of interest using MockPy. We have authenticated data access using Data Central's CAS server for authentication. Each user that is logged in may belong to a particular group, for example, a SkyMapper group, and that allows us to provide seamless data access control based on group membership. For example, and so what we do, for example, for SkyMapper is we select the individual TAP and SIA servers depending on that group membership. So if they're Australian and have access to SkyMapper DR3, we provide that, otherwise DR2. And there's a lot of possibilities here with the authentication. And here you can see a SkyMapper image and TAP catalog displayed together. We developed DAS also as a test bed for pipeline as a web service technology, which we have developed in terms of reducing AAT data with 2DF. We use Celery underneath to prepare and schedule complex workflows to produce image mosaics. And on the bottom right here, you can see one of the workflows that we have. We have an initialization stage, then we download several files at the same time, different images, and then combine those, project them separately, and then combine them. So we've been doing this for SkyMapper, Gemini, and VLT4s. But launching these workflows is not easy. Single service queries are very easy to do from asynchronous functions. It's just a retrieval of a VO table. But for the heavier pause jobs, it can be a bit difficult. And we need to schedule these asynchronously. So we have a case of async inception here, where we use Celery, which is an asynchronous task manager, from an asynchronous function. The problem is Celery is not async IO compatible, and you do not want to wait for Celery task results and process what the outcome of a task is from an asynchronous function, because it will block or hang your entire program. So the workaround we use is to launch Celery tasks from asynchronous functions using task.delay. And that runs off in the background. From the task, we can post to an endpoint that we've set up using WebSocket, and then use WebSocket messages to raise errors and notify on completion. This shows you some VLT4s 2 mosaics that we make on the fly for NGC 6302. And the gray bar here is just the result of the mouse cursor moving over the list, the table of images. And as you move your cursor over, they are updated in the Aladdin Light display, allowing for a very seamless user experience. For larger images, we can add buttons to trigger downloads manually and provide a progress bar. Some of the Hubble WFPIC 3 images are very large, so they take a little bit of time. The architecture that we've developed for DAS is it can be repurposed to develop more sophisticated applications. This one we have developed is a target visualization and classification application. And we can, in this application, we import CSV targets into a Mongo database, and we can classify those targets using keyboard shortcuts or radio buttons, and then export the results. We use Aladdin Light to display each target individually, and you can also add catalogs on top of that and instrument footprints. The catalogs can be loaded up asynchronously using the same technology from DAS, and you can filter catalogs internally with the Pandas data structures as well. I'll be talking more about this next week at the Interop. But for the meantime, Michelle's talk earlier this week on the machine learning applications is really exciting as a possible application for this application, where you take candidates of interest, refine their classifications using this application, and then send the results back to the machine learning model. So I hope I've shown you a glimpse of DAS. It's a powerful and extensible platform for data discovery and visualization, especially for archival data using our pipeline as a web service platform. We hope to expand this pipeline as web service to reduce other spectroscopic and imaging data from multiple observatories. And this will really open up a new era of visualization and downloading of reduced data products without having to touch raw data or install pipelines, which is really quite innovative, I believe. We plan to improve table handling. At the moment, we just have some HTML tables, but there are some JavaScript packages that we can use. And these will allow users to customize column order and load up tables quicker. We may experiment with cross-matching of tables. I already touched upon briefly the authentication that we provide. And this allows us to customize data sources depending on the user and their profile. For example, if they belong to a private survey team that has data available, we could make that available. We want to develop more themed profiles as well, radio data, time domain data, and incorporate other visualization packages such as a spectrum viewer that we have developed at Data Central, and perhaps even larger data formats. Yes, thanks, I'm done. Of course.
Thank you very much, Brent. Looking for some questions coming through. Anyone in the room? Sorry, Brent. David Buckley is typing. Let's give him a second. And stopped. All right, well, perhaps we should move to the next talk in anticipation of the final. Okay, great. Let's. Brent, sorry, we've run out of time, so we need to move to the next talk, but there are some questions coming through, and so please keep your eye out on Discord.
Will do.
And thanks very much once again.
Thank you.
Right, so our final talk for this session is from Jimenez Esteban, talking about European Virtual Observatory Schools.
I will do. Can you hear me?
Yes.
Okay, I'm sharing the screen. Okay, hope you can see my presentation. Okay, so I'm Francisco Jimenez Esteban. I'm a member of the Spanish Virtual Observatory Group. And today I'm going to tell you about the Virtual Observatory School that actually we organize in Europe. So in this talk, I will first tell you about the EuroVO and the ESCAPE project. Then I will talk about the Virtual Observatory School. I will explain the approach that we follow on the schools, and I will end talking to you about the training material that we have prepared along these years, and where can you find this material. So the EuroVO is actually the Virtual Observatory network in Europe. It started 20 years ago, and currently it comprises 6 national partners. We have Astrogrid in United Kingdom, we have the European Space Agency, and the German, French, Spanish, and Italian virtual observatories. The EuroVO initiative has been always funded by the European Commission through different projects dedicated to the Euro Virtual Observatory itself, or as part of larger collaboration, which is the case of the Asterix and the ESCAPE project, the 2 last projects. So in the case of the ESCAPE project, which is the project which is currently running, it's running since 2019. This project tried to bring together 3 different fields in the research, which are actually interlinked, which is the astronomy, the astroparticles, and the particles physics. And the role of the Virtual Observatory on this large collaboration is to bring the huge experience on standards and protocols to create the European Open Science Cloud. So actually, there are 6 institutes, European institutes, that participate in this project. If you want to learn more, don't miss the talk by Marco Molinaro tomorrow. So the schools, since the beginning, we realized that there is a necessity to introduce the astronomers, the European astronomers, into the VO. So we have organized schools since 2009, every 1 or 2 years. These schools are mainly focused on the early career astronomers. But if there is enough space, the senior astronomers are also welcome. Typically, we have among 30 and 50 students per schools, which give a total number of more than 400 students along these years. The number of tutors participating in each school is also very high. There is a rate of about 1 tutor every 3 or 4 students. So the students and the tutor has a very close contact and can work very closely together. In the past, the schools were in person. However, with the global pandemic, the rules changed. So in 2021, we have the first virtual school using the online platforms like Zoom or Slack for offline question and discussions. We actually don't realize of a lack negative impact on the learning, and at the end of the school, we get a very good evaluation by the students. So thanks to this experience, we have decided to keep both participation in the next school. We recover the in-person participation at the same time that we keep the online participation. And the following school will be in the early next year. The approach that we follow try to reach two main goals. The first goal is to try to train the students in the current virtual observatory tools and services. So the idea is at the end of the school, the students will be able to use the virtual observatory into the daily research. So for this, we train the students in tools like Aladdin, like Topcat, Estil, or VOSA, and introducing the CDS portal or also the ADQL languages. And there is a second goal, which is also very important, which is to gather direct feedback on the tools, on the service, and on the school itself. So the idea is to have a first-hand opinion on the necessity of the astronomers to try to incorporate this into the virtual observatory. So the format that we typically have is first we have a series of short introductory talks that takes no longer than 2 hours. And then we have about 5-6 hand-on sections of about 2 hours each. This is really the bulk of the school. Each session is guided by one tutor, which is then the main tutor that guides the whole group. However, there is also 2-3 backup tutors that give support to individual students in a specific moment when some issue arises. At the end of the school, or to end the school, the last day is dedicated to the scientific cases proposed by the students. So before the school, actually, we contact the student and ask them to prepare a scientific case and send us the scientific case so we can make some preparatory work with the students to see which is the best approach to work this scientific case within the VO. So the last day, the students can work together with the tutors on their own scientific cases. To end the school, we made a survey asking about the tutorials, whether they were difficult or not, whether there was useful tutorials, or whether the allocated time was the appropriate or not. But also, we asked about the school. We normally have a very good rates, and you can see most of the people think that the school are excellent or very good. And also we ask the students to the future plans, whether they will use or think that they will use the virtual observatory in their daily research. And normally most of the people say that yes, they are willing to use the virtual observatory in their research. And about the training material, we try to prepare all training material based on real science cases. For example, this is the training, the tutorial dedicated to the VOSA tool. And this material is, or this tutorial is based on this paper. This paper was Stanson et al. In 2017 that analyzed a group of stars to obtain the masses and the sizes of the stars. So we use VOSA to also analyze these stars and to obtain the same parameters, but within the virtual observatory. At the end, we compare the results of obtaining using the virtual observatory tools and the result published on the paper. And the tutorials are very detailed tutorials and explaining step by step. So the idea is that the students can be able to follow the tutorial with a very little help, or even without any help at all. So also, we provide the tutorial to the students so they can repeat the tutorial later at home, or have the tutorial for a review in the future. And for the tutorial, we have collected the tutorials in several repositories that are actually publicly accessible, and that can be found in the site of the EuroBO or the STERIC project. There is also a repository in the Spanish Virtual Observatory website. And I want to mention that there is also a collection of tutorials dedicated to not for research, but a lower level for education, to be done in high schools, for example. So with this, I finished the talk. Thank you for your attention. And just if you are a research working on an European institute, remember that you are welcome to the next Virtual Observatory School, and the registration is open if you are interested in. Thank you very much.
Thank you very much, Farhan. Yes, looks like very, very interesting and useful resources there that I have noted. Questions on Discord or on the floor? I don't see anything coming through at this time. Beg your pardon? Yeah, previous talk. Okay, if we don't have any other questions, let's thank Frank and all the speakers from this session again, please.
Thank you very much.
Before everyone goes to the in-person delegates, Oleg just wants to make a quick announcement about tonight's dinner.
Right, folks, you've seen the program. The conference dinner is going to be at the Two Oceans Aquarium. That's just a short walk away down here on the waterfront. It starts at 7. There's going to be a live music event, so don't be late. And there's also going to be drinks and things. So again, don't be late or they will all be gone. And to the remote participants, all I can say is I'm sorry for you. Sorry about that. We will see you on Thursday. And we're done for the day. See you at dinner. Thanks very much.